All right. So today we're going to be talking about thermal actuation. And before we jump into this, I want to briefly review heat transfer. So there are four different possible mechanisms for heat to move from one point to another. The first of these is what's called thermal conduction. So in thermal conduction, we have heat transfer through a solid medium in the presence of a temperature differential. Next, we have natural thermal convection. So natural thermal convection is heat transfer from a surface into a stationary body of fluid. And in this case, a temperature gradient in a fluid induces local flow movement through buoyancy. And the fluid movement facilitates the heat transfer. Our third method is forced thermal convection. And it is heat transfer to a body of moving fluid. And what we'll find is that the bulk fluid movement provides enhanced heat transfer as compared to natural thermal convection. And then our last method of heat transfer is radiation. So in radiation, we have heat transfer through some form of electromagnetic radiation. Propagating in either a vacuum or air. So each of these different mechanisms have different mathematical relationships that describe the heat transfer process. Okay. So we'll go through the governing equations now. So the first one, let me just write this out as equations. So I'm going to have Q double prime sub COND. And this is standing for conductive heat flux. Measured in watts per square meter. Is going to be equal to negative capital K times the derivative of temperature with respect to position. So this K is the thermal conductivity measured in watts per meters times Kelvin. And this equation describes heat conduction along a given axis. So if heat is traveling along the y-axis, then we would have the derivative taken with respect to y, etc. Okay. So I think realistically in a three-dimensional system, that derivative of temperature with respect to x would actually look like the vector gradient operation for what it's worth, but you're not going to have to deal with anything like that. Our next relationship is going to be Q double prime CONV for convection. That's going to be equal to H times, excuse me, that should be a T. TS minus T infinity. So let's define some things here. Our Q double prime in this case is the convection heat flux. Once again, measured in watts per meters squared. This H right here is the convective heat transfer coefficient. Measured in watts per meter squared times Kelvin. And then TS is our surface temperature. T infinity is our fluid temperature. And this equation is for natural and forced convection. Where the only real difference in these cases is the value for each. So putting together a little table here. So this bit will be for natural convection in both gases and liquids. And our H values, and these will all be in watts per meter squared Kelvin. So in gases, we might see numbers ranging from 2 to 25. In liquids, this is significantly higher. So we might see 50 to 1,000. Okay. For forced convection, again, we can break this down into gases and liquids. Gases are going to be about 10 times stronger, so 25 to 250. Liquids ranging from 100 to 20,000. And then lastly, we've got convection with a phase change. Meaning that we are either boiling our material or experiencing some form of condensation. And here we have ranges anywhere from 2,500 to 100,000 for our convective heat transfer coefficient value. Okay. So as was mentioned in the description, natural and forced convection are effectively the same thing, just force has some sort of fluid movement inherent to it that makes that heat transfer stronger. And so we have much larger heat transfer coefficients in that case. Our last equation is going to be for radiation, where we're going to have E is equal to epsilon, which is not going to be permittivity, sigma, which is not going to be conductivity, TR to the fourth power. So defining things here, we have our emissive power, measured in watts per meter squared. This epsilon is radiative emissivity. And this is going to be a number ranging between 0 and 1. So 0 radiative emissivity means that it holds heat extremely well, so it doesn't give anything up, it simply absorbs it. Radiative emissivity of 1 means it very easily gives all its heat away to the surroundings. Then sigma is going to be the Stefan-Boltzmann constant. Having a value of 5.67 times 10 to the minus 8 watts per meters squared times Kelvin to the 4th power. And then lastly, we have TR, where this is our absolute surface temperature measured in Kelvin. And this equation, again, governs radiation. So we see these 4 heat transfer mechanisms everywhere in our daily lives. Okay? So as a simple example, I'm going to attempt to draw a pot of boiling water. So something akin to this. So here's my, excuse me, crappy pot. There's the surface level of the water. And then down here, we're going to say that this is an electric stove. And so these black circles here represent our heating coil elements. So essentially, down here on the bottom, we've got some coil temperature, typically very hot. And then up here at the top, we have our ambient air temperature, right? So there is very much a temperature differential in the system. So what we'll see is we are going to have simple conduction. Our heating coil is transferring heat into the assumedly metallic surface of the pot itself, right? So that's heat transfer through a solid, so that is simply conduction, right? Thermal conduction. Well, we're also going to see that we have some convection, right? So we've got convection here because we have transfer of heat from the solid surface of the pot to the liquid inside of the pot. Okay? We're going to have some convection up here because we have our bulk fluid transferring heat into our air. So that's essentially fluid to another fluid. So that's convection. We are going to have heat transfer from the surface of the pot to the surrounding air. And then we are also going to have radiation, radiative heat from our heating elements out into the air as well. Can you go around the floor all the time? The pot is going to some of its heat is going to get transferred to the surrounding air. Convection, yes. So let me just write these out. So we have conduction, convection from solid to liquid, here we have convection from liquid to air. Here we have convection from solid to air. And then lastly, we have radiation over here.
Why is 5 radiation?
So we have essentially an electrical signal that is causing those guys to heat up. So that's why I'm considering that to be radiation more so than convection. But obviously, it is made of some material that's going to be releasing energy out. So I'm saying that because it's electricity doing the work there, we're going to call that radiation. Because radiation depends on propagation of electromagnetic fields through a medium, which is all what electricity is. But you could very easily say that it's the surface of those things getting hot that is convecting into the air as well. And just as similarly, you might say that number 4 there is blurring the lines between convection and radiation as well, since it's the surface of the pot just dumping energy out into the surrounding air. You could just as easily argue that that might be radiation as well. So anyway. So heat transfer occurs whenever a difference in temperature exists or a temperature gradient exists. Okay. The ability of a medium to transfer heat between 2 points can be quantified by its thermal resistance. So the greater the thermal resistance between 2 points, the smaller the heat transfer rate will be for a given temperature difference. So if we considered a longitudinal rod, right? So something like this. with some length L, some cross-sectional area A, and some thermal conductivity K, right? So if there's a temperature difference across the ends of the rod, then our total heat flow due to conduction would be our heat flux times area, right? And if we look back at our units of heat flux of watts per meter squared, multiplying that by area should give us our heat measured in watts, right? Well, since we're dealing with conduction, right, and we have an equation for that, this would be negative K, our thermal conductivity, times our area, times our change in temperature across essentially the change in length of this system, which is just L. Well, this expression can be rearranged to look a lot like resistance. Okay? So we could say that our thermal resistance in this system is going to be the magnitude of our change in temperature divided by our heat conduction, which would be 1 over K times length over area, which is essentially analogous to the relationship resistance R is equal to 1 over electrical conductivity times length over area. So let's work an example using this concept. So let's say that we have a resistive ohmic heater. It is located in the center of a suspended fixed beam. So something akin to this. So we've got essentially our substrate here. And then here's our beam on top. So our substrate is essentially acting like a heat sink. We've got our beam on top, and then on top of that, and I'll do this in gold, we're going to have a metal strip like so. A metal strip like so. And then connecting these two metal strips is going to be our heater. And I'm going to draw this heater as if it was a thin serpentine piece of metal, much like the heating element in your stove or on a space heater or something like that. So that when we pass current through that really thin wire, it's going to transfer heat to everything around it. Okay. So this bite right here is metal. This part right here is our heater. And then this gray bit down here is our beam. That's kind of a top-down view. And then for a side view, we might look at it something like this. Here's our beam. On top of our beam is our metal. So let's give this thing some dimensions. And let's say that the width of our beam is this guy right here, and it is 10 microns. This is the thickness of our beam, and it's 0.2 microns. This will be the width of our metal strip, and it is 8 microns. And then we're going to have the thickness of our metal strip, and it'll also be 0.2 microns. So the beam is made of silicon nitride, which has a thermal conductivity of 5 watts per meters Kelvin. And the metal leads are made of aluminum, which has a thermal conductivity of 240 watts per meter Kelvin. The beam is 10 microns wide, which we've already covered. It is 100 microns long. And 0.2 microns thick. We already have that. If the input power to the heater is 0.1 milliwatt, and we want to know what is the heater temperature, assuming the substrate maintains a temperature of 27 degrees Celsius. So I'm going to attempt to draw a picture, almost a circuit representation of this thing, right? So up here at the top, I'm going to have the temperature of my heater. And from an electrical circuit standpoint, this is going to be the point of highest potential in our system, right? So this is the hottest place in our system. And then down here at the bottom would be our lowest point of electrical potential or our lowest temperature, right? So our temperature heater of our heater is essentially playing the role of maybe a voltage, and the temperature of the substrate is kind of playing the role of ground, okay? So connected between these 2 points in our circuit, we're going to have some thermal resistances. Okay. So if we look at this, we're looking from our heater towards the outside. Okay. So to me, on the left-hand side, I'm going to see a metal strip between the heater and the substrate, and the beam, or half of the beam between the heater and the substrate. And I'm going to say this, see the exact same thing on the other side. So I'm going to represent this like 4 resistors in parallel. So here I'm going to have a metal strip, a beam, another beam, and a final metal strip like this. So the thermal resistance of the beam is just going to be 1 over the K value for the beam times our length over our area, which is going to be the width of the beam times the thickness of the beam here. So 1 over KB is going to look like I'm going to have 5 watts in the denominator, and then a meter times a Kelvin up here in the numerator. So my length, I'm going to put in, so the overall length of the beam is 100 microns. So I'm going to say that halfway across, since we're going from the heater, which is at the midpoint to the left, and then from the heater, which is at the midpoint to the right. So I'm going to call this 50 microns up here. My width is 10 microns. And my thickness is 0.2 microns. And so I should wind up getting 5 times 10 to the 6 Kelvin per watt as a thermal resistance here. For my metal strip, similar thing, 1 over Km times my length over Wm Tm. So 240 watts per meters times Kelvin. Again, 50 microns up here. And then this guy's going to be 8. This guy's going to be 0.2. And I should get about 1.302 times 10 to the 5 kelvins per watt. And hopefully that makes sense because we should see that our metal has a lower thermal resistance because it's got a much higher thermal conductivity. So the equivalent thermal resistance in this case is just going to be twice Rm, or 2 over Rm, 2 over Rb, and then all of this to the -1 power. So that's just 1 over Rb plus 1 over Rb plus 1 over Rm plus 1 over Rm, all of that taking the reciprocal of it because it's just 4 resistors in parallel at this point. And I should get, throw this in my calculator. Plus 2 over 1.302, 10 to the 5, to the -1. 6.345 and some change times 10 to the 4 kelvins per watt. And so using this value, the temperature of our heater is simply going to be the temperature of our substrate plus our input power times our equivalent thermal resistance. So that would be 27 degrees centigrade plus 0.1 times 10 to the -3 watts times 6.345 times 10 to the 4. So I'm going to say that since Kelvin and degrees Celsius are literally the same thing, I'm just going to call this degrees C per watt. And we wind up getting a delta T, so the temperature difference of 6.344 degrees, so plus 27, 33.34478, so let's call it 345 degrees Celsius. And this is assuming that we have no heat loss due to radiation or convection to the air. All right, so let's talk about heat storage. So in many devices, the speed at which the temperature of a microstructure can change is critical. So the thermal resistance influences the response speed of a thermal actuator. So you may recall from our class meeting on, I believe, Friday when we were talking about piezoelectric actuation, and I mentioned that it happens instantaneously. Well, this is a case where it very much does not, right? It takes time for heat to be transferred. And so it's going to take time for our actuator to respond to that change in temperature. Okay. So the mathematical relationship that relates our stored thermal energy and the temperature change is as follows. So we're going to have Q, our thermal energy in joules, will be equal to SH, which is our specific heat, measured in joules per kilogram times a degree Kelvin, multiplied by our mass, measured in kilograms, times our change in temperature. And we can rewrite this as CTH, which is our heat capacity, measured in joules per Kelvin, multiplied by that change in temperature. Well, this heat capacity is analogous to electrical capacitance. Okay. And from this, we can determine a time constant using our electrical analogs for a heat transfer system. Okay. So I'm just going to make a note here. Analogous to electrical capacitance. And then from this, our time constant, tau, is going to be our thermal resistance times our heat capacity or thermal capacitance, which we could write out or expand as our thermal resistance times our specific heat times the mass of the object that we're heating. Okay. All right. So now let's talk about actual thermal actuation. We spent the last 52 minutes or something doing background stuff. Now let's get into it. Okay. So we could cover thermal bimorphs again under the constraint that now we are applying a change in temperature, not measuring a change in temperature, but all of those relationships are going to be exactly the same. So I'm going to gloss over that because we covered it in thermal sensing. Okay. Instead, let's talk about thermal actuation with a single material. So essentially what we're going to have is a displacement generated due to material expansion. Or if we have anchored both sides of a beam or something like that, instead of having thermal expansion, we might see a large force generated that's pushing against the boundaries that are holding or keeping our beam from expanding, okay? So something akin to this, right? So we've got a beam here in the middle that has some temperature gradient across it. Like so, right? So in this system, where this is our x direction, the strain produced in our x direction should be alpha, our coefficient of thermal expansion that we talked about when we were dealing with our stuff in thermal sensing, times our change in temperature. Okay? Nothing real wild or crazy there. However, if we don't allow the material to expand, the strain, total strain, must be zero. Okay? So what we should find is that we're actually going to have this thermal strain and then our induced strain in the system are zero, which means that our stress is going to be negative Young's modulus times our coefficient of thermal expansion times our change in temperature. And we can say that the force that's acting in the x direction is just going to be the cross-sectional area of our beam times this stress. So we'd get E A alpha delta T. And so we'd see that we can usually generate pretty large forces for very small displacements. Right? But what if we need a large displacement with a thermal actuator? So this is one of my favorite things I've ever seen in MEMS. It's really, really interesting to me. We're going to do geometric amplification. Okay. So let's consider if we had a chevron actuator. Okay. So think about it like this. I've got some anchor point down here. And then I've got a long beam like so. And then I'm going to have a mirror image of this guy on the other side, or as close to a mirror image as my peon brain can make. Good God. So this is our original length of our beam L. like so. And then yeah, this situation. So this height is going to be y naught, L naught, and x. Okay. So the not subscripts there are for what our values for these things are before we heat this bad boy up. Okay. So we should see that our strain is just going to be alpha times delta t, right? This thing can expand, so it's not going to be too bad there. And then our change in our length is just going to be our strain times L naught. So what we're going to do is we're going to use some very basic trig for this guy, okay? So when this guy heats, my length L naught is no longer going to be just L naught. It'll be L naught plus that change in temperature, or that change in length, right? So that's my hypotenuse of my triangle. So I can say that my hypotenuse, L naught plus delta L squared, is going to be equal to my base of my triangle squared times the height of my triangle squared, right? So the base of my triangle is just going to be x squared. And the height of my triangle is now going to be y naught plus delta y squared. And I'm going to expand this guy out. So I'm going to have L naught squared plus should be twice delta L times L naught. Don't know why I'm missing that there. Plus delta L squared on this side. And on the right-hand side, I'm going to have x squared plus y naught squared plus, let's see, twice delta y, y naught plus delta y squared. I believe I've expanded that out right, all that kind of good stuff. Okay. So we know that for these thermal expansions, the change in length should be relatively small. So when I square that term, it's going to look incredibly small compared to the original dimensions of the thing. So I'm going to say that we can neglect that term and that term because they're so much smaller than the L naught squared term and the Y naught squared term originally. Okay. So neglected because they're small. Well, this x squared term, right? So that x dimension isn't going to change. Essentially, what we're going to see happen is we look at the forces generated by this guy, right? So this guy is going to generate a force like this. This guy is going to generate a force like this. And our horizontal components cancel out. So my net force is only going to be directly up, right? So I can use the fact that since x doesn't change, I can say that x squared, looking at our original system, is just going to be L naught squared minus y naught squared. So L naught squared is equal to x squared plus y naught squared. Rearrange that guy. Again, it's just Pythagorean theorem, right? Putting that substitution in, I get L naught squared plus twice delta L, L naught is going to be approximately equal to L naught squared minus Y naught squared plus Y naught squared plus twice delta Y times Y naught, right? Well, minus Y naught squared plus Y naught squared, those guys go away. L naught squared on the left-hand side of the equal sign and an L naught squared on the right-hand side of the equal sign, those guys go away as well. This common factor of 2 cancels this common factor of 2. And rearranging this guy, what I find is that my change in Y is equal to L naught over Y naught times my change in length. So my change in the Y direction can be much, much larger than just the simple expansion of my beam if my ratio of L naught over Y naught is very large. So I get pure geometric amplification in this system. I think it's a really, really neat way to do stuff. Okay. So another way that we can have a thermal actuator using only a single material. So these are kind of interesting to me as well. I don't have any math behind them, so we'll just talk about generically kind of how they work. Okay. So we can also use asymmetric actuators. So our first structure might look something like this. So if we passed a current through this thing, right, it's going to cause stuff to heat up. But we've got one long leg and one very short leg. And the long leg should expand significantly more, right? Because while the strain through both of them is going to be the same due to the heat transfer, we're going to see more thermal expansion out of the longer leg because its initial length is so much longer. So if the long leg expands more than the short leg, what we'll see is that it winds up essentially creating a torque and causing this guy to push out to the right, like so. So this is the direction of our displacement. Another way we can do something similar to this is have two legs that are the same length, but one of them has a larger cross-sectional area. So we might have a situation like this where I've got what would be called my hot leg. And then I've got this guy over here, which is my cold leg. So if we think about the thermal resistance of each of those legs, right? The cross-sectional area of the hot leg is much lower than the cross-sectional area of the cold leg. So the hot leg will have much less thermal resistance and therefore expand more. And so we'll once again see a displacement directed off to the right like so. So it's again exploiting geometry in order to get movement in a particular direction based on opposing thermal expansions. Okay. All right, so that is enough out of me for today.